All right. Hello, everyone, and welcome to the final Physics 328 video. So that's exciting. What we're going to do today is we are going to talk about the stability of a rigid body rotation. And this is the last section of Chapter 11 in Marion and Thornton. Okay, so what we're going to do is we're going to consider the case of force-free, so there's no torques acting on our rigid body, and so these are going to be rotations of a rigid body about one of its principal axes, about one of its principal axes. And so because we are going to specialize on this case of free rotations and rotations about a principal axis, the analysis is actually going to be pretty simple, because what will happen is we will have a simplification of Euler's equations of motion because there's no torque, and the angular velocity omega will be along one of the principal axes, and so that is going to make a further simplification, and we'll see how that develops just in a moment. So the problem that we will attempt to look at is an examination of the stability of such rotations. So in particular, if a small perturbation is applied to, say, the omega vector, the angular velocity, what happens? So let's imagine we're rotating around one of the principal axes, say the first one, so that omega is just equal to omega 1 in the E1 hat direction. And then we slightly tilt the angular velocity vector away from that E1 hat direction. Does that perturbation grow? Or does it get dampened? Or does it result in small oscillations about the dominant rotation axis direction? So does one does the perturbation get damped, or does our system oscillate about the dominant rotation direction? Dominant rotation. So if that's the case, we're going to call that a stable rotation. Another possibility is that those perturbations away from one of the principal axis directions just start to grow as time evolves. And if they grow, we'll call that an unstable rotation. So does, I guess we have the does already. The perturbation does the perturbation get enhanced with time, i.e. does it grow? And if it grows, we'll call that an unstable rotation. So you may recall that one of the simple demos that we did in the first class at the beginning of term was you just take your phone and its principal axis directions are pretty obvious. There are three axis, like your phone is a flat kind of rectangle, and so one of the principal axes is along the long axis of the phone, one of that's perpendicular to the phone but through the center of mass, and then the third axis is perpendicular to those two. And if you flip your phone around those three axes, you should find that two of the rotations are stable and one is unstable, and we're going to try to do that analysis. So you should try that with your own phone, and I don't take any responsibility for damaged phones. Okay, so we consider a rigid body with three distinct rotational inertia about the principal axes. Okay, so we have I1 not equal to I2 not equal to I3, and we're going to make the choice that we'll take the third principal axis to be the one that has the largest rotational inertia. And then we'll take the second one to be the one with the second largest, and then the final one will be the principal axis with the smallest rotational inertia. Okay, so we start our analysis with a body rotating about the first principal axis. So this is going to be the rotating about the E1 hat direction. Okay, and so if that's happening, then what we have is that omega is just equal to a single component in that direction. Okay, so if we had our phone, for example, the three principal axes of our phone are, here's one of them, and that's the E3 hat direction. That's the largest rotational inertia. And then there is an axis along the long axis of the phone. And so this is the E1 hat direction. And so that's the one that has the smallest rotational inertia. And then there's a perpendicular one that comes out through here. And I guess if I wanted to make a right-handed coordinate system, I'll put the E2 hat direction in that direction. Okay, and so we're just going to say, let's take our phone and rotate it so that it's spinning about the E1 hat direction. Okay. So we next imagine that we apply a small perturbation or a small disturbance to omega such that we still have our dominant rotation about the E1 hat axis, but then we allow for some small contributions along the two other principal axes, where we're going to make mu2 and mu3 both much less than omega 1. Okay, so that's our definition of a small perturbation, is that the components in the along the second and third principal axis are small compared to the component along the first. Okay, so to go further, what we're going to do is we're going to recall Euler's equations of motion, which looked like n1 was I1 omega 1 dot minus I2 minus I3 omega 2 omega 3, and then something similar for the other two, I3 minus I1 omega 3 omega 1, and then n3 is I3 omega 3 dot minus I1 minus I2 omega 1 omega 2. Okay, so I want to point out one thing while we're here, and that is that in the first equation, we have this term where we have I2 minus I3. And the third equation, we're going to have an I1 minus I2. What we did is we assumed that I3 was going to be biggest, I2 was going to be in the middle, and I1 was going to be smallest. And so that means this I2 minus I3 is going to be a negative number because we're going to take I3 and subtract it from I2, and I3 is larger. Likewise, I2 is greater than I1, so over here, I1 minus I2 is going to be negative. On the other hand, over here we have, let me change the color for emphasis maybe. What we have is an I3 minus I1. So in the N1 and N3 cases, our difference of rotational inertia was a smaller one subtracted by a bigger one. In the N2 case, it's the larger inertia subtracted by a smaller one. And so this was going to be positive. Okay, and so that's going to be really important as we go through and finish this analysis. But let's just make that emphasis right now. Okay, so for free rotations, and with omega 2 equal to mu 2 and omega 3 equal to mu 3. And so changing the notation from omega 2 to mu 2 and omega 3 to mu 3 is just really to remind us that the components of omega along the second and third principal axes are small. Okay, and so what do we get? We're going to get n1 is 0, and then we'll have a, if we solved for omega 1 dot, what we would get? We'd get I2 minus I3 divided by I1, and then omega 2, omega 3 is going to end up being a mu 2, mu 3. Okay, and then for n2 equals 0, if we solve for omega 2 dot, that's going to be a mu 2 dot, and then we'll get a I3 minus I1. We'll divide by I2, and then omega 1 stays as omega 1, and then omega 2 becomes a mu 2. And then finally for omega 3 dot, that becomes mu 3 dot. Then we get I1 minus I2. Then we'd have to divide by an I3. We would have an omega 1, and then omega 2 becomes mu 2. I've made a mistake over here. For N2, the omega 1 stays as omega 1, but then omega 3 becomes a mu 3. So this needs to be a mu 3. Okay, then I think that should be correct. Okay, so the first thing we can do is we can deal with the first one. Since the product mu 2 times mu 3 is the product of two small numbers, since this is very small because let's get rid of the since. We'll just say mu2 times mu3 is very small because it is the product of two small numbers. Okay, so therefore, to a good approximation, what we can do is we can neglect mu2 times mu3 such that the first equation becomes omega 1 dot is approximately 0, or omega 1 is equal to a constant. So if we set our rotation to be predominantly about the E1 hat axis, then that component of the angular velocity omega 1 remains about constant. Okay, so then we have the remaining two equations. And so let's call this equation 2 and this equation 3. And then I guess we could label this as 1, although we've already dealt with that one. So what we'll do is we'll first take a time derivative of equation 2. So let's take a time derivative of 2. So we'll get a mu2 double dot, and then inside the brackets we have I3 minus I1 divided by I2 and an omega 1. Those are all constants, right? We just showed that omega 1 should be about constant. So when we take the time derivative, we'll just get a mu3 dot. Okay, so we have mu2 double dot is equal to I3 minus I1 over I2 omega 1 mu3 dot. And so maybe you can see what we're going to do is we're going to take equation 3 and sub it in for mu3 dot. And when we do that, what we get is I3 minus I1, and then mu3 dot has an I1 minus I2. I1 minus I2, and then we have I3, and so we have I2 times I3. They both have a factor of omega 1, so we'll get an omega 1 squared. And then the mu3 dot, sorry, it kind of froze on me here. I can't, okay, are we back? I can draw, but okay, sorry, we're back. So mu3 dot has a mu2 in it, so we should get a mu2. Okay, good. What I'm going to do is I'm going to recall that what we had was I3 was the biggest rotational inertia. So this I3 minus I1 is positive, and this I1 minus I2 is negative. So in this one, I'm going to reverse the order of I1 and I2, and I'm going to rewrite this as minus I2 minus I1. Okay, so if I do that, then this thing in brackets is positive, and then we get a negative sign out front. Okay, so then this should be equal to minus, and what do we get? I3 minus I1, which is positive. Then we get an I2 minus I1, which is positive. Divide by I2, I3, omega 1 squared and multiplied by mu 2. Okay, I'm just going to rewrite exactly the same thing because we're going to start a new page here. So I3 minus I1, I2 minus I1, I2, I3, omega 1 squared, mu 2. So everything in the square brackets, I'm going to define that to be an omega 2 squared. The subscript 2 is just to remind us that this applies to mu 2. And that quantity, whatever it is positive because we arrange the difference of rotational inertia in the numerator to both be positive. All right, and so therefore what we've got is mu 2 double dot is equal to minus omega 2 squared mu 2. And we've seen this kind of differential equation many times now, especially if you think back to Physics 216, we did oscillators a lot. And the solution is, one way to write the solution is that mu 2 is equal to some coefficient e to the j omega 2t plus b e to the minus j omega 2t, where j is the imaginary constant square root of minus 1. Okay, so let's just do a little check just for the sake of it. So we take one time derivative of mu 2. That brings down a j omega 2 for both terms, except for the second term we get a minus j omega 2. So we could write that as j omega 2 a e to the j omega 2t minus b e to the minus j omega 2t. And then if we take a second time derivative, we get another factor of j omega 2. So we get j squared, which is minus omega 2 squared. And then we get e to the j omega 2t. We'll pick up another minus sign for the second term. And so it becomes plus b e to the minus j omega 2t. But this was exactly the form of our original solution. And then we get 2 time derivatives of mu 2 is minus omega 2 squared times mu 2. And that was exactly what we were supposed to get. Okay. So we've got the solution for mu 2, and omega 2 we know is positive. Well, okay, sorry. What we actually know is that omega 2 squared is positive. So therefore, if we were to take the square root of that, omega 2 could be plus or minus something. But whatever that something is, it's a real number. We didn't have to take the square root of a negative number, which would result in something that would be imaginary. Okay, so omega 2 is real, therefore our solution represents oscillatory motion. Is oscillatory. Let's say oscillatory motion with a frequency given by whatever omega 2 comes out to be. So just as a reminder, these complex exponentials we could write as trig functions in the following way. And so those trig functions clearly represent oscillatory motion. So what that means is that we'll get our rigid body to be predominantly rotating about the E1 hat axis, but there will be some oscillations along the E2 and E3 directions, and the size of those oscillations will be determined by the size of the original perturbations, but they're not going to grow. Okay, so there's no growth of the perturbations that were away from omega equal to omega E1 hat. Say omega 1 E1 hat is the way we wrote this. And so what we get are stable oscillations. Okay, and so that's our first observation, is that if we start a rotation about the axis with the smallest rotational inertia, we will get stable oscillations. And so that means if you take your phone and you start rotating it about this axis, then what you'll find is that you should get stable rotations. Okay, so next, let's do the same analysis for a perturbation to rotations about, let's do the E3 hat direction. Okay, so now what we're going to have is omega is going to be equal to, say, mu1 E1 hat plus mu2 E2 hat plus omega 3 E3 hat. Okay, and again, mu1 and mu2 are small. We could do this a bit quicker because everything's going to be very similar. The equations of motion are, from Euler's equations, going to be mu1 dot is equal to I2 minus I3 over I1 omega 3 times mu2. Mu2 dot is going to be I3 minus I1 over I2 omega 3 mu1. And omega 3 dot is going to be equal to I1 minus I2 over I3. Then we'll get this product of these two small quantities, which we're going to say is about 0. And so we'll get omega 3 is about equal to a constant, just like last time we did for omega 1. Okay. Following the same analysis as above, we're going to get mu1 double dot. So let's take the derivative of the first term, and so we'll get a I2 minus I3 divided by I1, and then we'll get a mu2 dot, and from mu2 dot we get an I3 minus I1, and it's divided by I2. Both of them have an omega 3, so we'll get an omega 3 squared. And then from the mu2 dot we'll get a mu1. Okay, I3 minus I1 is positive, but I2 minus I3 is negative. So I'm going to write this as minus I3 minus I2. And then we'll get that mu1 double dot is equal to minus I3 minus I2, I3 minus I1, I1, I2, omega 3 squared mu1. And like we did before, we could define this as, say, an omega 1 squared. And the way we've written it, the two differences in the numerator are positive, and so this is a positive quantity. And we will find that mu1 solution is oscillatory motion of frequency given by omega 1. So this is exactly the same situation as before, and so we would get stable oscillations. What we can say now from the two cases we've studied so far is that rotations about the principal axes with the smallest and largest rotational inertia are stable rotations. Sorry, I should have said here, not a stable oscillation. It is a stable oscillation, but really what we're trying to talk about are rotations. So these about a principal axis, stable rotation. All right. So at this point, you may have noticed that what I did, so for example, in this case, we came up with a solution for mu1, but we haven't bothered coming up with a solution for mu2. If you did that, and I do recommend that you do it, it's exactly the same type of thing that we just did. We would take a time derivative of mu2 dot. That would give us a mu2 double dot times some constants times mu1 dot. You'd sub in for mu1 dot from the first equation of motion, and you would solve it, and you would get a solution that has mu2 oscillating, and its oscillation frequency would be exactly the same frequency that we calculated for the mu1 case. Same thing if you went back to the first problem that we solved. In the first problem, we solved for mu2, but we didn't bother solving for mu3. If you did it, you would get the exact same solution that we got for mu2, and the oscillations would have exactly the same frequency that we calculated for mu2. All right, so finally, what we have is one more case to consider. So finally, let's repeat this analysis for an angular velocity that's predominantly aligned with the second principal axis. All right, the procedure is the same. We start with Euler's equations of motion. We're doing the free rotation case, and we would get mu1 dot is equal to I2 minus I3 divided by I1 omega 2 mu3. And we would get omega 2 dot is equal to I3 minus I1 divided by I2 mu1 mu3, which we would say, let's neglect that, and we'd get the usual thing, omega 2 is a constant. So that nothing changed there. And then we have mu 3 dot is going to be I1 minus I2 divided by I3 omega 2 mu 1. Okay. So let's take a time derivative of mu 1 dot. So we'd get mu 1 double dot is going to be equal to I2 minus I3 over I1. Omega 2 is a constant. Then we get omega 3 dot. So we sub in for omega 3 dot from above. And what do we get? We get I2 minus I3, I1 minus I2. Then we divide by I1, I3. We get 2 factors of omega 2. And then from mu 3 dot, we get a mu 1. Okay, here's where things are going to get different. Previously, what we had is in these types of equations of motion for, say, one of the mu parameters, it always involved the second Euler equation of motion. And that was important because this I3 minus I1 was a positive quantity. And so we had that positive difference in rotational inertia multiplied by a difference in rotational inertia that ended up being negative, say like an I1 minus I2. We don't have that in this case. We have an I2 minus I3, which is negative, and so we might say, look, I want to define what I think is going to be a positive squared quantity for some kind of frequency that we want to define. So I2 minus I3 is negative, so let's write that as minus I3 minus I2. And then we look over here and we say I1 minus I2, well, that's also negative. And so let's write this as minus I2 minus I1. In the previous cases, we only switched the order of one of those differences of rotational inertia. We've done it both times in this case, and so the two negative signs end up canceling, and what we get is an I3 minus I2 times an I2 minus I1. Both of those differences are positive. And then we have some other constants in here, mu 1. And for emphasis, let me put in that this is a positive sign out front. If you look back at the other cases that we analyzed, that was a negative, and so that's really important. Okay, nevertheless, we go on and we say, well, okay, so what we could do is we could say this is going to be an omega 1 squared. Let's define that as omega 1 squared, and it's positive like it was in the other cases. And so our differential equation for mu 1 is, again, for emphasis, let's say it's plus omega 1 squared mu 1. So the solution in this case, the solution is mu 1 is equal to a e to the omega 1 t plus b e to the minus omega 1 t. There's no j in these exponentials. They're not complex exponentials anymore. They're just straight up exponentials. So we could check that the solution works. We take one time derivative. We're going to pull down an omega 1 for the first term and a minus omega 1 for the second term. and then we take a second time derivative. We get another factor of omega 1 for the first term, and another minus omega 1 for the second term, so that becomes plus. But this thing in square brackets here is exactly the assumed solution for mu1. And so mu1 double dot is equal to omega 1 squared mu1. And that's exactly the differential equation that we had. Okay, so in the solution then, what we have is one term representing exponential decay. And so that one we don't really worry about, because it says if we had some kind of perturbation, then that perturbation just decays away. And so that would be nice. That would be stable rotations. But over here, we have an exponential growth. So if omega 1 is positive, then we have this mu1 with a term that just grows very rapidly with time. Again, if you did this analysis and solved not for mu1 but solved for mu3, you would get exactly the same type of solution. The omega 3 in the exponential would be exactly equal to the omega 1 that we calculated in this case. Okay, so therefore, for rotations about the E2 axis, the second principal axis, which is, we're going to call that the intermediate axis, because it is the axis that has the rotational inertia that is between the large and small ones. For this case, the perturbations grow exponentially. And so this results in an unstable rotation. And so this is sometimes called the, I don't think our book uses this term, but I think this is sometimes called the intermediate axis theorem. So if you take your phone and so here's your phone is something like this, right? And so the intermediate axis is the one that goes through the center of mass in this kind of sense. Can probably do that a bit better. And so this is, say, the E2 hat direction, rotations about this axis. If you had your omega predominantly in that direction, where this is rotational inertia I2 that's between I1 and I3, this would be unstable. And so what unstable means is that, you know, if you did an absolutely perfect, flawless flip of your phone where there was no disturbances in either, no components of omega in either the, along the first or third principal axis, then it would just rotate about that second principal axis nicely. However, that's really impractical. No matter how good of a toss you do, there's always going to be some imperfections. Those imperfections will grow exponentially, and the flip of your phone will not be a nice clean flip. And so you can go ahead and try that as many times as you like. Okay, so so this is our intermediate axis theorem. Unstable rotations around the axis that has the middle rotational inertia. So let's think of an application. And so I want to consider a skateboard. I'm not a skater and I've never been, but this is actually a pretty interesting example. So let's see if I can draw a skateboard. I want to try to draw this with, well, okay. I mean, it's not a great drawing, but you get the idea. Okay, so the skateboard has three distinct principal axes. Here's the axis with the smallest rotational inertia. So to be consistent with our analysis above, we'll call that the first principal axis. And then there's an axis that has the largest rotational inertia, and we'll call that the third axis. And then there is an axis with the intermediate rotational inertia. And so we'll call that the second axis, and rotations about that second axis have rotational inertia I2. So here we've selected the principal axes such that, like above, I3 is the largest, I2 is the intermediate, and I1 is the smallest. So if you did rotations about the E1 hat direction, they would be stable. So for skateboarders, one of the things they try to do is the kickflip, and that's a rotation about the axis with the smallest rotational inertia, and that's stable. Okay, so a rotation about the E3 hat direction is also stable, and I'm sure there's a name for it. I have no idea what it is. So that's a spin where if you're looking down at the board when you're on it and you did a rotation about E3 hat, you would see it do kind of a 360 where the long axis of the board would be rotating. Okay. However, rotations about the E2 hat direction are unstable. So if you take your board and you try to rotate it about this axis, where you just kind of flip it up somehow and let it rotate about that axis, it will be unstable. It won't be a clean rotation. And they do have a name for this, and it's called the impossible. And so that's actually a good name. People do this trick, but what they have to do is they have to leave their foot. They use one of their feet to guide the board, so the board rotates along their foot, and the foot is used to stabilize the rotation, to suppress any of the perturbations that might come about. So to successfully complete an impossible, skaters cannot let the board rotate freely. They must have the board rotate about their foot, and this foot is used to suppress any small perturbations to the angular velocity direction. So we want that angular velocity to be along the second principal axis. And you want to suppress those perturbations because if they exist, which they always do, they will grow exponentially. Okay, good. So actually, in the description of this video, I've linked a few other YouTube videos. One of them is a physicist talking to one of the most famous skateboarders to ever exist. And so they talk about this intermediate axis theorem. And so it's kind of fun. It's not too technical, and so it's worth a watch. Another one of the videos is a really good short video of someone doing a really clean impossible, and it's in slow motion, and so you could see their foot actually guiding the board as they try to rotate about the second principal axis. And then the third video is one that's fairly well known. It's some tool out in space. Maybe I didn't check carefully, but I assume it's on the International Space Station. And they get this tool spinning, and you can see the unstable rotations where it flips back and forth between kind of two stable rotations, but it's unstable because it's flipping between the two. And so that's really kind of an amazing thing to see, and it's really not intuitive, but I think it's relevant to what we've been talking about. So anyways, that's worth checking out, those short videos that are linked in the description. And with that is a wrap for Physics 328. I've tried to make these videos as useful as possible, and so I hope they are a good resource for you. Keep an eye on the course website for any updates about the exam, and I still will post a sixth assignment that you won't be handing in, but I'll give you an assignment so there's some problems that you can look at and try. I will also post my solutions. And then I've also updated the website to include all of the assignments from last year and their solutions, and as well as the midterms and final exam and their solutions from last year. Okay, so that's a wrap. Thanks very much, and we'll talk to you later.